Hi everyone, welcome to our second video in our motion and forces unit. Today we're going to be talking about how we can measure motion. So we've already been talking about how we can tell whether something's moving or not, and we talked about using point of view and reference points to tell whether something's in motion. So in this picture, we know that Usain Bolt is in motion because we can use the people behind him as a reference point since they're still. The question is, how can we tell if something's moving slow or if something's moving fast? We know these things are moving, but how do we know how fast or slow they're moving in relation to each other? To calculate something that's related to how fast or slow an object is moving, we're going to use speed. Speed is calculated by distance over time. So as an example, let's say that KD runs 90 feet down a basketball court in a total of 30 seconds. If that's true, then his speed would be 3 feet per second. Just divide. This would make sense because KD is a really fast runner. This is a really helpful diagram that will help you to calculate speed, distance, and time. We use this pyramid to help you with that. At the top is distance, that's the D, the S is speed, and the T is time. If things are next to each other, you're going to multiply, and if things are on top of each other, you're going to divide. Now, let's talk about a different measurement called velocity. Velocity is similar to speed, but not the same. Velocity is a vector, just like this guy. In Despicable Me, when Vector says he commits crime with both direction and magnitude, he is actually describing a scientific vector, which is any measurement that has both a direction and a magnitude. Speed is not a vector because it's missing the direction piece. So when we talk about velocity, velocity is just speed in a direction. So if we were going to calculate velocity, we could say that when we talked about KD's speed was 3 feet per second, that's a speed. We could make that a velocity by saying 3 feet per second toward the goal. Then it becomes a velocity. Speed in a direction. We're going to be looking a lot at graphs that look something like this, and this is distance over time. So we talked about how distance over time already is speed. So the slope of this graph is showing you the speed of the object. So in this situation, distance is increasing and time is increasing. This is moving at a constant speed. These red bars are showing you that the object didn't change distance. So in this situation, it stayed at 12 kilometers between the seconds of 12 and 14. So in this situation, the object is at rest. Sorry, that looks a little messy. Now, let's talk for a second about this portion of the graph. The slope is pretty steep, so we can estimate that the object is moving fairly fast, but it's returning from a distance of 12 kilometers back to 0 kilometers. So the line is going down, but the speed is still positive. The speed, it's still going a constant positive speed, a fast speed. What's important about this is that distance is not the same as displacement. So to calculate the total distance that this object traveled, we would add up all of these different segments. So this would be a distance of 3, this is 0, this is from, let's see, 3 up to 12, so that is 9, and this is from 12 to 0, so that's 12. So in this situation, the total distance is 3 plus 9 plus 12, which is a fairly high number. Let's see, 3 plus 9 is 12, that's 24 kilometers. The displacement, though, is how far away the object is from the start when it gets to the end. So the object started here at 0 and ended here at 0. We're talking about distance, not time. So the total displacement is 0 kilometers. So distance and displacement are different. Here's an example of some different distance and time graphs that you might see. So you can see if the line's curving, that means it's slowing down. If it's curving upwards, it's getting faster. A linear solid line is fast if it has a steep slope, or slow if it has a less of a slope. And then a flat horizontal line is at rest, which means that there's no motion, it's not moving. Now, another measurement that we want to talk about is acceleration, which is change in velocity over time. We also can have deceleration, which is the same as acceleration, but it's negative. So as an example, let's say that this ant was originally moving 3 centimeters per second, but now it's only moving 1 centimeter per second because it got tired, and it slowed down in a time of 2 seconds. So we could do this math up here. So this would be 2 centimeters per second over 2 seconds, and we would get an answer of an acceleration of 1 centimeter per second squared. So change in velocity over time. Here's an example of another graph. It looks a lot like the one that you saw before, but pay attention to your y-axis. This is the y and this is the x. This is showing you that the speed over time has increased. So this is acceleration. This is no change in the speed, so this is constant speed. So important to note that this is a horizontal line, but this object is not at rest. It's still moving at a constant speed because we're looking at velocity over here. Now this is deceleration because the slope is negative.